Okay, so now we discuss about the physics biasing for hadronics. You will have a lecture on what is biasing after me, where you will understand many of the things. So I'm trying of anticipating an application of what you will hear later in general and with some example in electromagnetic. Here, I'm concentrating on hadronics. So biasing is a way to get the results more quicker than in the normal way, which is called analog or unbiased way. So this is the old approach. So what before this generic biasing that you will learn in the next lecture has been introduced with version 11.0, so 12 years ago. These were the built-in biasing possibilities that were present in hadronic, and still they are present, but not all of them recommended to be used. One is the radioactive decay. We have seen in the hadronic physics too that there are UI commands, several UI commands to use biasing radioactive decay. For a cross-section, there is the possibility to scale an hadronic cross-section by calling this method, G4 hadronic process by a CrossSectionByFactor, where you specify, for instance, 1,000. I want to increase the cross-section by 1,000, for instance. And suppose that you want to include to enhance the muon-nuclear, you just call like this with 1,000 there. The problem is that it's not trivial to get this muon-nuclear process. And I will show you some code how to get it. And then there is the leading particle biasing that it is also, so I will describe later what it is. Okay, so the modern way, so for radioactive decay, I think it's still okay to use this UI command for radioactive decay, so the one that we have seen in the hadronic physics 2 lecture. For cross-section, you need to write some code. I will show you quickly how. So it's possible, it's not ideal, but definitely for the leading particle biasing is too complicated in practice. So I will not even tell you how to do, because there is a better way that we will see in a second. So for instance, if we want to use this native hadronic way to bias cross-section, this is the way. For instance, in your main program, after that you specify the physics list, for instance, FTF-BERT, you register my special physics constructor. So when you see something starting with not G4, it means that it's something special, something your application, my application in this case. It's not something distributed with Gen4. All the Gen4 classes, they start with G4. Okay, and this is the way to define this class. It inherits from this G4 physics constructor. And then you have construct particle where there is nothing to define, and you need to define construct process. And there you need to get for instance, we want to bias the muon minus cross-section, in hadronic cross-section. So we ask the process manager to get all the list of processes for mu minus. Then we loop on these processes. And when we found the process that we are interested in, muon-nuclear in this example, we take it. So this is the inelastic process that we are interested in. And then we call this bias cross-section by a factor. So it's not a huge code, you see, but you need to write something. Whereas there is a better way with this generic biasing. So for the leading particle bias and many other things, it's much simpler and neat to use the generic biasing approach that will be explained in the next lecture. And you can do much more. You can do cross-section biasing, force collision, geometry-based biasing, including possibility to use parallel geometry. You will understand all this better later. And hadronic model per region. So I will show you some examples. So the underlying explanation, as I said, will come to the last lecture. So let's see this new approach. There is a directory, example extended biasing and example extended hadronic, where you see some of this that I want to show you today. So we will see these 4 examples very quickly. There's plenty of code, but this boilerplate code that you don't need to modify, you don't need to understand line by line, but you can easily reuse. And I will show you only a few lines where you eventually need to put your hands if you want to adjust for your case. So the first one in this subdirectory is GB for general biasing 01 is for the cross-section biasing. The second one is to force collision. I will explain you what it means. Then we have this famous leading particle biasing, and I will tell you what it is. And then we have in this directory, example extended hadronic, hadr08, which shows how to get hadronic model per region. So there's plenty of code. I will go quickly. So because as I said, there's not the point to understand line by line. An important thing to keep in mind, whenever you're using biasing, you have to keep in mind that the weight of the particles or tracks, if you want, is not 1. It's a number which is different. And you need to
Hi, sorry to interrupt. We lost the room again.
The question in a second.
Yes.
So the question is, how is the weight assigned?
Yes. So it is, let's say, done automatically by Gen4. You shouldn't care. Whenever you use one of these biasing scheme, especially this generic biasing that we recommend to use, automatically the weight is properly propagated by the inside Gen4. The only thing that you need to worry is to take this weight that you get from the G4 track class, where there is the method getWeight. So whenever you have a track, you ask the method getWeight, and that is a number that then you feed to your histogram, centuple, and so on. But it's automatically propagated by Gen4, by the system automatically. Okay, so let's see quickly this cross-section. So the idea is I'm interested to a particular process, which naturally, let's say in nature, is pretty low, and I want to enhance it because I want to study it, and I'm interested on that. So suppose that I want to boost the cross-section for gamma and neutron. The same can be for other particle or for only one for them, okay? So you see, after where you specify the physics list, FTF BERT in this example, you use this physics constructor, G4 generic bias in physics. And there you specify which particle you are interested, like this, so a few lines. And then at the level of detector constructor, where you specify the sensitive detector and field, you define things like shown here. You again specify which particle, and this is the important thing, you specify in which logical volume you want to bias, because it can be convenient for you to bias only in particular region, typically, not everywhere. So you can define, if you want, the biasing only in specific logical volumes. This is the class, you see GB. So this is a class, an example of this example. It's not a general class of geom4, which start with G4. So when you see GB, it means general biasing is this example that we are going to look. Here we build a map where for each particle that we want to bias, we have to have this operator change cross-section. This generic biasing consists of defining operator, and then operator deals with operation. You will see in the lecture after that. So here in the add particle, you basically instantiate this operator change cross-section by specifying the particle name. And then there is given that altering the cross-section means that you are altering with respect to what is happening naturally, how frequently that interaction occur, the method which is somehow important is called propose occurrence biasing operation. You see that here it returns a G4. So this is something in geom4, not in this example, biasing operation. And here you can put some if statement if you want to limit the application of biasing. So for instance, you could apply biasing only for primary particle, not for secondary. This is just an example, it depends on the application. Or you can apply biasing only to the first maximum 5 interaction, and then you want to continue naturally, not biasing anymore. Or you want to stop the biasing when the weight becomes too low, because then you can be subject to fluctuation and you need to run high statistics. It becomes a bit tricky. You will see in the next lecture, you will have a bit of understanding. So this is a proposed occurrence biasing operation, is a place where you could put your hands in order to customize when the biasing is applied. And here is where you define the operator. We change the cross-section from one particle. You see that in red, it's from a geom4 class, a virtual class, G4V biasing operator. And yes, and okay, this is, let's skip it. The point is that in this proposed occurrence biasing operation, here finally, there is the method set bias cross-section where you can put the factor that increases, typically you want to increase to scale the natural cross-section. So, and here it is supposed to be the same for all the particles, in our example, gamma and neutron, but you can imagine that by putting an if statement, you can use a factor of 10 for neutron and a factor of 20 for gamma, for instance. You can have different things. Okay, another type of biasing is so-called forced collision generic biasing, which means that suppose that you have a thin target and most of the particle will go through, will not interact in that thin part. But you are actually interested only when there is an interaction occurring, for instance, an hadronic interaction. So you can use this biasing where you are sure that there will be an interaction in that thing. But you are biasing, so you have to remember that you have this weight to keep track of. Currently, it formally works perfectly for neutral particle, but not for charged one. The reason is the charged particle decrease by ionization, they lose some energy. So the treatment must be slightly different, but for a thin target, you can apply it also for charged particle because the approximation is really good. There is no problem, basically. And in the current form, as it is, but there is a way to change, it basically treats, suppose that you have a neutron and you want to force an interaction of a neutron on a thin target of silicon, let's say. This means that one of the processes associated to neutrons will occur for sure in that thin target. But therefore, they are elastic, capture, fission, and inelastic. So as it is right now, it happens one of these four, but there is no way there is a way if you put the hands to have only one, for instance, only inelastic, not the other one. So it keeps the fraction of the different processes as they are in nature. So you're sure that it will happen, but not you don't have a way, at least in this format, to specify which of the four processes in this example. So here is the same thing. You see, you can specify the type of particle and the logic volume where to bias is exactly as before. Here again, you inherit from this G4 biasing operator. This is a multi-particle class. So it means that you have this map with a set of particles that you want to bias. And for each of them, you define a G4 biasing operator force collision. And actually, when you add a particle, you instantiate this operator that forces the collision, specifying the name of the particle, essentially. And again, in this proposed occurrence biasing operation, I didn't write anything here. You can add, as before, some limitation when to apply biasing, as before, basically. And that's it. So there is, as I said, there is code, but you can take it and use it as it is. And the only place that you eventually might add something is in this proposed occurrence if you want to use biasing in a special way. I was mentioning this leading particle generic biasing, which is still present in native hadronic, but is complex to use, and we don't recommend to use, but you can use the generic biasing approach. So let me explain what it is. Leading particle is useful for shielding application, where essentially you take the most energetic, when there is an interaction, a number of particles are produced, you take the most energetic one, and then you pick one particle of each category, like, I don't know, pions, for instance, or baryons, and so one instead of, and you drop the others. And this is a way somehow to get the results in these deep shielding problems quicker, essentially. And there are also options to make it even more refined by using a Russian roulette, etc., but it's not showing this example. And you will see what is this Russian roulette method in the next lecture. So again, the beginning is the same. Let's suppose now that we want to bias only proton and only inelastic in particular. Again, there is the possibility to specify the volume where you want this leading biasing to occur. You define an operator leading particle by inheriting by the usual G4V biasing operator. You create this operation leading particle object, and in the constructor, you see it is instantiated, this operator leading particle, and then yeah, and that's it basically. So again, it does everything is automatically done. So if you go in the code, you can use it, and you can slightly modify things to customize to your application, basically. So, but this is really specific for a shielding application. It's not. Yeah, the last one that I want to show you is a bit an unexpected thing that we were not actually thinking at the beginning when the generic biasing was introduced. Is a nice way to use this powerful machine of generic biasing to essentially get a hadronic model per region. So you know that essentially in Geom 4, you have one physics list which is applied everywhere. There is no physics list per region. However, for electromagnetic physics, you can specify different model for different region of your detector, only for electromagnetic model. This is not possible in the hadronic framework for hadronic models. So you cannot use in one part FTF, in another part QGS. So the hadronic model has to be used everywhere. However, by using this generic biasing, it's possible actually to achieve this hadronic model per region without changing the hadronic framework. And I will show you how. This is a real concrete case which came from ALICE. So they wanted to have to use a more sophisticated intranuclear cascade, the INCL, instead of the default Bertini in the tracker part, because they realized that it describes better the data, the experimental data. However, if they use FTF PINCL physics list instead of the FTF BERT everywhere, in particular in the calorimeter where there are plenty of interaction, plenty of particles, their simulation will slow down by a factor of 2. So by using this trick of generic biasing, they get exactly what they want, so a more detailed description in the tracker part by using INCL, but for the rest of the detector, they were actually using FTF BERT and without essentially any CPU overhead. So, and by the way, here, the weights remain 1. So it's generic biasing, so we are using this machinery, but we are not altering anything. I will show you in a second. So the weight here is still 1. So it is de facto unbiased, if you want. But we are using the machinery behind the scene. So again, suppose that is for proton. In their case of ALICE, they were using for proton, neutron, pi plus, and pi minus. Here, to be brief, we use only for proton. We define this biasing operator like this, and we decide to apply in the tracker. So we want to apply this thing only on the tracker. And as you see, sorry, we start with FTF BERT. So FTF BERT is our physics list, and we want to apply this special trick only in the tracker to have something slightly different than FTF BERT only in the tracker. So we have to define this biasing operator class, inheriting from G4 biasing operator, as in all other examples. And here we are not altering the occurrence because the cross-section will remain unchanged. We don't touch the cross-section. We want to change the final state. And there is this method proposed final state biasing operation. So what we want to bias is the final state, but it's a biasing with weight 1, because what we are doing is replacing the final state produced by the Bertini internuclear cascade model with the final state produced by the INCL, so more sophisticated intranuclear cascade. And yeah, so here in this proposed final state biasing operation, basically, we check that if we are dealing with proton inelastic, instead of using the proton inelastic, which comes with FTF BERT physics list, we are returning our biasing operation. And our biasing operation essentially defines essentially, you will see now here in the constructor, we define an inelastic process for proton where we give the models of INCL instead. So when it comes in that volume, which is the tracker, for a proton interaction, instead of using the proton inelastic of the FTF BERT physics list, it will use the special one, which has been set up to use the INCL. So we are biasing the final state, but replacing one model to another, and the weight remain once, and we get exactly what we want, basically. And that's it, basically. And there is a couple of exercises for you if you want, just some suggestion for you if you want to do some exercise on this generic biasing. So many of these things will be much more clear in an hour when there will be the lecture on this generic biasing, but the person who actually implemented this generic bias in Geom 4, Mark Berberi. Okay, so that's it from me.
So the question is more on the physics lists for a radioactive droplet emitting positrons, fluorine 18. If I use EM standard physics option 4 plus decay physics plus radioactive decay physics and optionally optical physics for scintillation in the detector, do I need any additional hadronic physics lists or hadronic physics modeling, or is it sufficient for medical applications?
Yes, should be sufficient. Should be sufficient, unless well, you want to describe also some low energy interaction of the eventual fragments if they have some kinetic energy. But yeah, what you mentioned are the main building blocks. Yes, they seems the most important one. Eventually, you might have some hadronic inelastic that you could describe with particle HP, but it could be that they do very little for depending on the energy of your application. Could be that they can be neglected.
Nevertheless, using a prepackaged physics list that has these inside may still be a bit more reliable in case you.
Yes, the idea, let's say in general, it's always convenient to start with something, let's say, rich in physics that you're sure that it will cover, probably too much. So you start with that, you run a limited sample, and then you start removing things that you are not sure if they are really needed and so on. You should see that the simulation will be faster, and then you compare that simulation where you start simplifying and removing pieces with the one most precise. And if you see differences, then it might be differences which are important. So you need to go back to the one more precise. Or if you don't see anything, it means that you are not sensitive. And then it's better if you use the one with less physics because it will be faster. So that is the general thinking. So if you are in doubts, just try and compare. And according to what you are carrying, the observable that you care, whether you see a difference or not, statistically, of course, because it will not all be identical, but if statistically you see difference, then you need to think if it's important, yes or no, and so on. So this is a bit the criteria the way to proceed.
So the question has been posed a couple of times about personal dose equivalents, HP10, 3, and 0.07 for the distance in millimeters from a skin surface. And the person is interested in these for application from KeV to MEV, asking about how to simulate them in the best way forward. For example, when you calculate HP 0.07 dose to skin, or the part of the skin which is below this 0.07 millimeters, would you use a slab of a detector of thickness of 1 micron? And reading that some people utilize detectors from 50 to 70 microns. 1 micron is a bit thin to measure an interposition.
Yeah.
Have very large statistics, but one would have to see how it's done in practice.
Yeah.
Detectors themselves are.
Yeah, I mean, I'm not a medical physicist, so I cannot actually answer very well. And as far as I know, Gen4 doesn't provide, let's say, automatically this kind of answer. So you need somehow to use the physics, and physics for sure we will be able to cover, and then try to get your scoring or sensitive detector. Where
was discussed
on
Wednesday, but I'm not sure whether we have this, whether something that would immediately respond to that. One of the things was what physics list is best to use, and I think it's the one that we've been talking about, option 4.
Yes, option 4 for sure for electromagnetic, and probably QGSP, BiasCrossSectionByFactor, or something like that for the hadronic part, which is the one which is used in medical physics. Yes, I also suggest you to have a look. We have several examples, and have a look to the example. We have also hadron therapy and see. So try to get an example which is as close as possible to what you have done, and have a look there what is used, and eventually you can ask to the forum, or you can contact the authors of that example, which is in the area, let's say, of medical physics, of dosimetry that you are interested in, to get a bit farther than on that.
Okay, I have a maybe slightly simpler question to answer. If I change the cross-section of a process in my simulation, does the cross-section of other possible processes become adjusted to conserve normalization? No. You are simply scaling up that particular cross-section and that's it. The rest remain unchanged. So of course the results doesn't correspond to nature, but is the point you want to study, for instance, the effect of a background that you know is very low, and you want to enhance just to see what is the effect and so on. So there is no general recipe. You have to be careful, but yeah, we will only scale, and it only affects that particular cross section. That's it. The rest remain unchanged. There is a question.
Thank you. So my question is related to biasing for neutral particles like neutrons. What is the difference between cross-section biasing and force collision biasing, and which one is better to use regarding inelastic interactions?
Yes, so cross-section biasing means that you enhance typically the cross-section. Instead of being 10 millibarn, you put 1,000 millibarn. You increase everywhere in your, suppose that you apply everywhere. So if you have a thin target, if you increase by a factor of 100, you certainly will see more interaction, but not necessarily you will have an interaction in that thin detector. If you use the biasing where you have this force collision, then you are sure that there will be a collision. Even if it's a nanometer, you will have for sure. So it's a bit different. So the cross-section biasing is when you are interested to something everywhere. You want to see a process that you are interested to be more visible, happening more often, everywhere. If you are only interested in a thin target, typically, to see something occur in that target and not anything else, then you should use the force collision one.
I see. So force collision is like a more automated way of cross-section biasing, basically.
Yes, more automated and more localized, I would say. More localized.
And I know that cross-section biasing is prone to like over biasing, so one can easily over bias their simulation. So is it also the case for force collision biasing, or is it not an issue?
No, it shouldn't be an issue. At least if you want to typically use it to study hadronic interaction, inelastic hadronic interaction. So no, in general, it's fine.
Thank you.
As far as I know, there should not be that problem.
Okay, I think it's time to take the break. So.
I just have a very quick question.
Sure.
Yeah, so you're talking about that thin layer, right? And I think I have very strong voice, so probably don't need this, but for the outside, okay.
Yeah, it's enough for us.
So when we were talking about the force collision generic biasing, you were talking about thin layers, right?
Yes.
So how thin this target could be?
But the realistic one, for instance, I was talking about thin target validation, are typically millimeters. Half a centimeter, a millimeter, 2, 3. This is the typical scale of the thing. For instance, an hadronic calorimeter, which is typically a meter and a half of everything, there you don't need any, naturally you will have everything, it would be stopped. So it is really typically when you want to have an inelastic hadronic interaction in something of the order of millimeter or even smaller if you want. But yeah.
Yeah, and the last one, so if I'm working with muon tomography, what would be the best list, physics list to use? The Bertini list or?
Muon tomography, which kind of energy muons are?
Yeah, like for the atmospheric.
The atmospheric one. Well, it should be the FTF-BERT, for instance. You could try this EMZ to see if your case, for some reason, you are particularly sensitive of electromagnetic effects and so on. But FTF-BERT should be fine.
Okay, thank you.
And of course, yeah, I didn't mention maybe. I completely forgot to say that one practical usage for a given application to have different physics lists is not only trying out finding which is the best one. That is certainly the most important thing. But once you have find the most important one for you, the one that you use for, let's say, production, it's useful to have also some variation to determine also the systematic error, to evaluate the systematic uncertainties on the results. So the experiment, for instance, they use FTF-BERT as their main physics list for large production. But then if they have some analyses which are sensitive to intranuclear cascade effect and so on, they try smaller statistics, some other variation of the physics list, where they use another binary, for instance, or NCL instead of Bertini to see the effect. So this is true in general. Whatever is your application, you first find what is the best physics list for your application, and then you can consider small changes of that to evaluate how much sensitive is your results on that choice. Could be electromagnetic, could be hadronic physics, whatever. Yes? Wait, we give you because there's the people outside. Me, I understand, I hear, but it's for the people outside.
My question is also regarding muon tomography. Is that a good idea to use FDFB and then change the electromagnetic to M?
Yes, I would say yes. It's worth to try. So I would suggest to try FTF-BERT EMZ, for instance, and comparing with FTF-BERT. So you will see that the time of the simulation will be much quicker without EMZ. So you look at the observables, the distribution that you care. And if you see differences, then you have to think of why there is this difference. It could be that you need to use the EMZ. If for what you are interested, you see the same, then there is no point to spend more time and use the slow one. But as I said, when you are in doubt, just try out. Because with a small statistics, not a billion of events, but even if you have neutrons, for instance, you say, should I have a detailed simulation or not? You take one of these HP, you try, you see that it's much slower, but then if the distribution that you are interested, you don't see effect, then you can drop them. So you can really, it's a kind of iterative process to find out exactly what is the best configuration. So there is no problem to try to go back something else. You have all these options that you can play with, electromagnetic and hadronics.
we will now